very much. So this talk is, I'm presenting it, I'm from RAL Space, which is a space science department within the Science and Technology Facilities Council. But this work has been carried out in collaboration with Bartington Instruments and NPL, National NPL as well. So I'd like to acknowledge their contributions to this talk, and also a lot of this work has been funded by European Space Agency under a contract. So also I'd like to acknowledge them. So the talk today, I'd like to just highlight two applications of gradiometers in space. First one is Payload for a space science mission, and also a second application for verification of magnetic cleanliness of spacecraft and spacecraft components before they actually get into space. I'll give you an overview of the design of the gradiometer, the prototype that we're currently developing and calibrating, which I'll also talk about, and I'll highlight a few highlights or a few points on future work and challenges. So, space magnetic gradiometers. The target application of the prototype that we're developing is the LISA NGO mission. So, LISA is a candidate L-class, so large mission for the European Space Agency, and the purpose of the mission is to act as a gravitational wave observatory. So in this cartoon figure, we've got a star system, or a co-rotating set of stars which are orbiting around each other at a very close proximity and generating gravitational waves. You can also detect supernovae, and you have three spacecraft flying in a formation, in a triangle formation, and they're separated by 1.5 million kilometres. And as a gravitational wave from a spinning set of a pair of stars passes through the constellation, the distance between each of the three spacecraft will change. We've got a set of very accurate distance measurements, some optical interferometers that are used to measure the distance between the spacecraft, and you can measure on the spacecraft down to a distance of 4 by 10 to the minus 11 metres. So if you divide 1.5 million kilometres by 4 by 10 to the minus 11, you've got an exquisitely high precision measurement of the distance, relative accuracy of the distance between the baselines, and you can then, as a gravitational wave goes through, measure the change in length and hopefully detect the event. Now, the events themselves happen. Gravitational waves will have variable spectral components, and LISA's interested in measuring down to below 1 millihertz, so down to 0.1 millihertz, which would be 10,000 seconds. So a period of rotation of the stars, for example, over 10,000 seconds would be detectable by this mission. This is a graphic from Astrium of the concept. So there's a telescope it's used to transmit the beams and receive the beams between the pairs of spacecraft. And behind here, in this cavity, is a test mass, and it's a cube of platinum and gold, and it's in space, so that there's no extraneous gravitational forces acting on that cube. So if you accurately measure the distance between the cubes, you've got you can measure the gravitational waves. The only problem is, with such a high sensitivity measurement, that anything at all which causes the test masses to move or accelerate will corrupt your measurement and your signal. So the project team are worried about things like cosmic rays. So if a galactic cosmic ray particle enters the test mass, it will have a cascade of nuclear events, and out the other side of the test mass will be a shower of electrons, and that will create a net charge on the test mass, and then any electrostatic fields within the spacecraft will then cause it to accelerate and corrupt your very precise measurement. So there's systems in place to compensate for that effect, and also similarly radiation, solar energetic particles from the sun can have a similar effect, and needs to be compensated for. And I guess the interest for today is magnetic disturbances can also cause the test mass to give an apparent gravitational wave signal. So the test masses are each about 2 kilos, platinum gold, but they still have remnant but very small magnetic properties. And this equation here shows what basically the spectral dependency of the magnetic field on the apparent signal. So without going into the details too much, the amplitude spectral density, i.e. the noise on a spectral plot, is a function of both the gradient of the magnetic field as well as the magnetic field itself. So LISA, the test masses, will be susceptible to not only the DC magnetic field around the test mass, but also the gradient of the magnetic field in the proximity of the test mass. So in order to in the data analysis reject that magnetic noise, it needs to be characterised. So the gradiometer we're working on is on the roadmap to providing that measurement capability. Second application of gradiometers is in verification of magnetic cleanliness. So a lot of the job of a systems engineer for working on space programs is not so much in the design of the hardware, it's the verification of the requirements, and it's a very onerous task. And if you've got a requirement on the magnetic field that's to be exported from any particular component of a spacecraft, then verifying it in the Earth's field is difficult. And on a spacecraft like this, which is the Solar Orbiter spacecraft, which is due to launch in 2017, there's probably millions of components on there. There's a pair of magnetometers on this boom, which is deployed behind the spacecraft, and the disturbance to those science-grade magnetometers from the spacecraft itself needs to be below the measurement noise floor. Verifying that in the presence of the Earth's magnetic field is a tricky job, and verifying it for the whole spacecraft and making sure that nothing slipped through the net is difficult. Of course, you can put it in a cancellation system, but putting a spacecraft this size in a cancellation system would require one which would even challenge PTB. So a gradiometer, because it's immune to a homogeneous magnetic field from the Earth, can be used to screen at both component level, unit level, and eventually at spacecraft level. And they can also be used with the application of inverse mathematical methods to make a measurement of the piece of hardware and then infer the number of dipoles and the distribution and the strength within the measurement volume. So that's the second application for gradiometers in space. So we're currently developing this magnetometer, gradiometer, and these are the main requirements for the system. The gradient field needs to be plus or minus 50 microtesla per metre, and importantly, it needs to be able to operate in the terrestrial environment. The noise floor requirements are mainly derived from the need to measure down to 0.1 millihertz for LISA. Just looking at some of the other requirements, the linearity is very important, and ideally we want to get better linearity than that, because the gradient measurement is a differential measurement, and any non-linearities in the response of the individual sensors will appear as an error in the gradient measurement. So that's another important requirement. Size is very, very important, and it needs to be low power as well, so that and low mass for eventual space application. And also for terrestrial applications, you want to have a small measurement baseline so you can measure locally around a test item. If we move into the space environment, moving from terrestrial application to space is not straightforward, and the rigours of the space environment introduce extra design constraints, radiation, vacuum, and temperature, and the mechanical environment are also added complexities in the design. So as Michael's already pointed out, we're making a measurement of the gradient, but also the flux vector, and thanks to Maxwell equations, we actually, to characterise the gradient matrix, we only need to measure 5 out of the nine components. So five components means 5 pairs, 10 sensors. So this is the arrangement of the sensors within our gradient head. So we've adopted a nomenclature to identify the particular sensors. So this pair, YYM and YYP, measure the gradient aligned with the y-axis in dB y dy component. So that's what it looks like. That's the arrangement of the sensors. We selected flux gates for various reasons. Mainly there's good heritage. MAG 648 sensor itself, which is the bedrock of the flux gate technology that's gone into this gradiometer, is compatible with the requirements of the gradiometer. Those flux gates are very compact, and they've got excellent linearity, low noise, low power. I'm sure Olivia could go on at length, but it's shown to be a good choice to date. So this is the gradiometer itself. That's a €1 coin. So you can see that the head itself is very small. These dots here are where the flux gates are mounted within the make-or block. We've got front-end electronics to buffer the signals so that we can have a long harness, and we're not influenced by any parasitics on the harness itself or EMI pickup. This is the gradiometer head mounted within the cube, which is used for calibration. And the readout electronics, because we need such a high dynamic range, we need to have 24-bit digitisation of the signals, and that's kind of okay for the terrestrial environment, but 24-bit sampling of data for a space application is going to be a difficult challenge to confront. So we're in the middle of the calibration itself at the moment. It's been done in the low magnetic field facility at Bushy House, and the tests that we're carrying out are permeing sensitivity, gain and offset, effects of homogeneous magnetic fields, gradient sensitivity, offset, cross-field sensitivity, sensor alignment. Now, this is the error. Temperature coefficients are being done in the low magnetic field facility, and the noise floor of the sensor at low frequency. This is the pretty hot off the press measurement of the linearity of the sensor in the X direction, and this is some gradient noise that we've measured late last year. And so future work. So these are I've thought of 3 different things which could be used to as conversation starters for the panel later on in the seminar. The first challenge for space magnetic measurements is calibration and testing for the flight environment. So the effect of the space environment on the performance of the sensor needs to be taken into account in the calibration program. So some of those are the effect of the vacuum environment, mechanical environment, radiation. But the thermal environment is actually one of the more tricky ones, and that's one of the most important effect to characterise on the sensor, because sensors just about every sensor has a coefficient of temperature dependence, and doing that in the facility is not a straightforward process. Compact, low power, low noise readout electronics is another challenge. So gradiometers inherently require a high dynamic range if they're going to operate in a terrestrial environment. So you need to have very low noise readout electronics and high digitisation precision. With a gradiometer, you need to bias and read out a larger number of channels than a vector magnetometer. So more channels, more power, more mass and complexity. And then these last two, the components that are available to a designer of a terrestrial electrical system is much broader than what's available for a space system. So if you look at what's available on analog to digital converters for space application, getting above 12 or 14 bits is difficult. Getting to 24 bits is well, there's none exist. So that's a difficulty, and quite often that problem is compounded because a space-approved component is typically rad hard, and if it's rad hard, then its bias currents and power dissipations are generally higher, and noise performance is often compromised by being rad hard. So that's the second challenge. And then third challenge is maintaining program continuity. Space programs, particularly space science programs, come along almost once in a lifetime, and maintaining continuity, the fact that they come along once in a lifetime means that you have a famine and feast work profile, that you've got a program coming up and there's a big flurry of activity to develop something, and then the program's launched and you need to continue the work if it's to advance. So I think the key to this is developing links between space and non-space applications, and using that much hated word of synergy is very important. So conclusion, gradiometers are a niche in a growing area of space technology, both for space science but also for ground testing. We're in the last throes of the program, and the prototype is showing good results, and the results should be on the street later this year. And the other point is that space magnetometry has a unique set of challenges. Thank you.